Let's do an application problem of graphing radical functions, and I'm going to show you a couple different ways of going about finding the solution to this problem. You can model the population P of Corpus Christi, Texas between the years 1970 and 2005 by the radical function P of x is equal to 75,000, the cube root of x minus 1950, where x is the year. Using this model, in what year was the population of Corpus Christi 250,000? Well, let's start the problem off by talking about it algebraically. In order to figure out what year, x, the population was 250,000, you would set the equation equal to 250,000. So then you have to ask yourself, okay, well, how do you go about solving this algebraically? First, you should divide by 75,000. I know you really want to subtract 75,000, but remember, the operation going on between the 75,000 and the cube root is multiplication. So to get rid of multiplication, you have to divide. And you're going to get something like 3.33. Then, after you get rid of this, to get rid of the cube root, you do the inverse operation to the other side of the equation. The inverse of cube rooting is cubing. And then the last thing I would do is I would take whatever that answer is and I would add 1950 to it. And you're going to get a decimal, but we're trying to approximate the answer. So you should get that x is approximately 1987, which is option C. Well, let me tell you another way of doing it. We can also do this on the graphing calculator. If you use the program Desmos, it is probably a lot easier to do this problem, but on the graphing calculator, you can plug it in one of two ways. You can either make y1 equal to 75,000 cube root of x minus 1950. Remember, the cube root function is under the math menu. Or if you like working in rational exponents instead of radicals, you could instead change this to be x minus 1950 raised to the 1/3 power. Both methods of typing it into your graphing calculator will result in the same graph. So whichever one makes you happier. In Y2, you would put your 250,000. Because what we want to know is, when are these two graphs going to intersect? This is one of my favorite ways of solving equations, using the graphing calculator to find a point of intersection. Well, when you put it in your calculator, you're going to have to change the window setting so that you can actually see the point of intersection. So this is what I used. I changed my x minimum to be 1970 and my x maximum to be 2020. Why did I pick those numbers? Well, first of all, the beginning year was 1970, so I knew that I wasn't looking for a year before then. And since my multiple choice answers only went up to 1990, I figured if I picked something in the 2000s, I'd probably be good. My y minimum, I made 0. The reason for that is because my output is a population, and you can't have negative population. And I made my y maximum 300,000 only because I wanted to find when my graph was going to be at 250,000, so I needed something bigger than that. So then when I graphed it, I found this. And then when I used my infamous second trace 5, enter, 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 the graph told me that x was approximately 1987.04, so I said, well, it must be 1907. In problem 5, we want to look at the graph of y equals 2 times the cubed root of x plus 1 minus 4. Now I want to remind you that this is a transformation on the parent graph, y equals the cube root of x. Now if you don't know what y equals the cube root of x looks like, you can graph it in your calculator. But I want to start with, it's going to be this particular graph shifted 1 to the left, down 4, and stretched vertically by a factor of 2. So I started by graphing the parent function just to help me out. I realize you can put this in your calculator in one full swoop, but I want you to see how the graph changes as you perform these translations. So here's the graph of y equals the cube root of x. And now here's the graph when I've moved it left 1 and down 4. The blue one is the one that's been moved left 1 and down 4, and it looks like it went left 1 and down 4. If you kind of look at this pivot point here, which is at 0, 0, it went left 1 and then down 4, and look, there's the pivot point. So now, when I multiply that original function by 2, the blue graph turns into the green graph, and look at what it did to the graph. We say that it stretched it vertically because it kind of made it go up and down a little bit faster. That's what stretching vertically does. It makes the graph go up and down a little bit faster. So the actual graph of the function is just the green graph.